Okay, in this section we're going to learn how to solve quadratic equations by graphing a couple different ways, one by hand, and then we'll also show how to do it using the TI-80 series calculators, because those tend to be more efficient with, at least with some of these problems. So a couple main goals, like we said, graphing by hand, graphing with something called a table, and I'll show you how to find that in the calculator, and then graphing with a TI-80 something calculator. So first of all, this right here, this is standard form for a quadratic equation. We've already seen that before. When you're being asked to solve something, there are kind of 3 or 4 different words that you can use here. So let's say we had this parabola right here. These 2 points that I'm drawing right here, these 2 red lines, those are called zeros because at those points, y is equal to 0. They're right on the x-axis, so y hasn't gone up or down, it's right at 0. They're also known as x-intercepts because that is where that's where the graph intercepts the x-axis. So that's another word for them. They're also called solutions because they solve the equation and they make it equal to 0. And they're also called roots. And the reason they're called roots is because if you're solving a quadratic equation like this, for example, you would solve it by taking the square root. So you have positive or negative 3. Those are the 2 things that equal that. So those are 4 different words for the same thing. Zeros, solutions, roots, and x-intercepts all mean the same thing. So let's solve this equation by graphing. We always start by finding the vertex. The vertex, you might recall from last section, is negative b over 2a. So a, b, and c are just the numbers in front of these. So a is the number in front of x squared, that's a 1x squared. b would be negative 3, c would be negative 4. So the vertex in this case would be negative 3 over 2 times a over 2 times 1, so that's going to be 3 over 2. Then at this point we make like a table of values basically, and our vertex always goes in the middle, so the vertex is going to go right here. 3 over 2 is the same as 1.5, and then we'll pick a couple numbers above and a couple numbers below. We might have to go, since we're trying to find where it equals 0, we might have to do that more than once. So notice I'm traveling the same distance to get from 1.5 to 2. I'm going up 0.5, and to get backwards I'm also traveling distance 1.5. And then from there we can use whole numbers. So let's go 2, let's go 3, let's go 4, and then the other way, let's go 0, and let's go negative 1. And hopefully that will give us enough. So how do we find the other values? We just start taking these numbers right here and plugging them in for y. Y equals that equation. So when we plug in, let's just go down the line, we plug in negative 1, we'd have negative 1 squared minus 3 times negative 1 minus 4. That's going to equal 1 plus 3 minus 4, so that equals 0. We have a point negative 1, 0. Well, we found a 0 there. Then when we plug in 0, we'd have 0 squared minus 3 times 0 minus 4. That's going to be negative 4. So we have a point at 0, negative 4. That's going to put us right here. When we plug in 1, we'd have 1 squared minus 3 times 1 minus 4. Again, I'm plugging them into this top equation right here. That's where we're plugging in the x's. This would be 1 minus 3 is negative 2. Negative 2 minus 4 is negative 6. So 1, negative 6 puts us here. Okay, then when we find the vertex, it's a little bit trickier because there's a decimal here. 1.5 squared minus 3 times 1.5 minus 4. Okay, that's going to equal 2.25. Let me just clear this stuff off here. 2.25 minus 4.5 minus 4. And that's going to wind up being, what's that, negative 6.25. So that right there is the value at the vertex, and that puts us about right here, in between negative 6 and negative 7. And here's the nice thing about quadratic equations, they're symmetric, so things on opposite sides of the vertex are going to be the same. So 1 is 0.5 less than 1.5, it's going to be negative 6. 2 is 0.5 more, that's also going to be negative 6. We just use different colors so it's easier to see here. This number is 1.5 lower, this number is 1.5 higher, so it's also going to be negative 4. And then finally we can reason the same way. Since negative 1 is 0, that means 4 would also have to be 0. Okay, so we're going to get these points right here, whereas 2, negative 6 is right here, and 3, negative 4 is right here, and then we connect the dots. And the solutions to this, or the zeros, are here and here, x equals 4 and x equals -1. Those are the two things that make this equation equal 0. So that's exactly what they want us to find. They want us to find the zeros. Okay, these are the three possible scenarios. You could have an equation that has just one zero, it touches the axis just once, or that one that we just did had two zeros, or maybe it never touches at all and then it has no real solutions, and we'll talk more about that later in this chapter. Okay. Solving this by hand, so again later we'll show how to do it on a graphing calculator, but solve this by hand. So first thing is we always want to put this in standard form, which looks like this. It means that it equals 0. So we can make this 0 by adding x squared and by subtracting that 14. So now we have 0 equals x squared minus 6x, and then 23 minus that 14 would be 9. And now let's make our table of values so we can find our vertex and so forth. So the vertex is always negative v over 2a, which in this case would be negative -6 or positive 6 over 2 times a. A is 1, so 2 times 1. So 6 over 2, that would be positive 3. And then we'll just go a couple above and below to see how far we need to go here. So 3 squared minus 6 times 3 plus 9. And that's going to equal 9 minus 18 plus 9, and that actually equals 0 right off the bat. So since that's a vertex, we're not going to be able to have any other zeros beyond that. It's not like you could have another 0 over here, then that wouldn't be a vertex. That would be some other point in the graph. So if the vertex occurs at 0, you really don't need to look for any other zeros. All we need to do is just get these points right here so we can actually draw the parabola with, we need usually 3 points to do that. So if we solve this out, 4 squared is 16 minus 24, because that's 6 times 4, negative 8, plus 9 would be positive 1, and this is also going to be positive 1. So we know this is going to open up because it has a positive a value, so it should look like this. And that's a case like what we just said. The only zero, the only intercept right there, the only x-intercept is x equals 3. So that's what that comes out to be, and we saw that picture right here on the left side. That's when you have one real solution. Okay, let's see what it looks like when we have no real solution. So this one says use a quadratic equation to find two real numbers with a sum of 15 and a product of 63. We don't know what these numbers are, so let's call them by variables. Let's call them x and y. So we could say the sum of x and y is 15, and the product means multiplying, and product x times y is 63. Okay, so this doesn't look like a quadratic equation, but here's what we can do to make it look like one. Let's just solve this for y by subtracting x from both sides. So we get y equals 15 minus x, and now we can do something called substitution. We can see a y right there, and we see that y is equal to this. So wherever I see a y, I will just substitute 15 minus x. Okay, and let's now make this look like a quadratic. We'll distribute, so we'll have x times 15 is 15x, x times minus x is minus x squared, and we like them to be in standard form, which means equal to 0. So we will subtract the 63 from both sides, and we'll just rearrange this. So we'll put the negative x squared in front, because that's usually how it is in standard form. Then we have plus 15x, and we have minus 63, and that's equal to 0. So now how do we solve this? Well, we can be a little bit hard to graph it, because 63, graph it by hand is hard, because 63 is a pretty big number. So let's just put this in the graphing calculator. So we go to our TI-84, we go to y equals negative, I click the negative button, not the subtraction button, that's important, negative x squared, and then what's the rest of our equation, plus 15x, and then we have minus 63. We'll go to zoom, and then we'll go zoom fit, just to zoom standard, I'm sorry, see if we get a good picture. And that wasn't a great picture, let's go to zoom fit. So again, we're looking for zeros, we're looking for solutions. I think zoom standard is better. And you can see that never actually touches the axis. Let's just zoom out a little bit so we can see that slightly better. This never actually touches the axis, which means that there are no solutions. It never touches. And if you think about it, what kind of numbers we're looking for? We're looking for numbers that add to 15 but multiply to 63. There are no such numbers. The numbers that add to 15 would be like 0 plus 15, example, 1 plus 14 or 2 plus 13, etc. Okay, you could try every single one of those numbers. None of them will multiply. No pairs of numbers will do both of those things at the same time. Add to 15 and multiply to 63. That's why when we graph it, there's no solution. Okay, sometimes you're not going to get a nice, neat number, so we can use something called the location principle, and I'll use an example for this. Suppose that you're kind of driving through, let's say you're on a map of the four corners right here, the 4 states that are kind of like a rectangle, so Utah, Colorado, New Mexico, Arizona. Suppose that you fall asleep in the backseat of the car, you're driving through Utah at a certain point, and then later you wake up and you're in Arizona. And the question is, what must have happened while you're sleeping? And the answer is, you must have at some point crossed the border from Utah to Arizona. Same thing occurs on a graph. If you're graphing these points, let's say I was graphing this point at -2, 3, which is right there, and then I graph this point at -1, -6. And notice what must have happened. If I connect these dots, I must have somewhere crossed the border, so to speak, crossed the axis where y equals 0. I don't know exactly where, but I know that it happened between -2 and -1. Okay, because right here I crossed from a positive number to a negative number, therefore I must have crossed 0. I know there's a 0 between -2 and -1. I also know that because that is a negative y, and that's a positive y is interchangeable with f of x, I must also have a 0 somewhere between 0 and 1. So that is how we can kind of narrow down the possibilities. So let's graph this again on a graphing calculator, and let's see where the zeros might be. So x squared minus 6x plus 4. We'll go to y equals, and we'll clear this out. We have x squared minus 6x plus 4. And to get the table, we would go to second, and then right above graph, there's a table, second table. If we look at this table, we can see that we go from, we have all these positive numbers, positive 20, positive 11, positive 4, and then suddenly we get a negative. Therefore, there must be a 0 between these two x values, between x equals 0 and x equals 1. So we're negative, we're still negative, we're still negative, negative again, and then suddenly we became positive, so there must also be a 0 between 5 and 6. We don't know exactly where, but that's okay. We know we've at least narrowed down the options. We're between x equals 5 and x equals 6, there must be 0. Okay, how do we solve things using a table? So let's graph this one, x squared minus 6x plus 2. So we have almost the same thing as the last equation, we just change that to plus 2. How can we solve this using a table? We can go to second table, and we know there's a 0 between 0 and 1 because we changed from positive 2 to negative 3. We also know there's a 0 between 5 and 6. So let's do this. So we can't tell, let's narrow down the options between 0 and 1. So we'll go to second table set, and let's go back to that for just a sec. So I know that I want to be between 0 and 1, so this time I'm going to go to second table set, that's above window, and I'm going to start my table at 0 this time. And this time, instead, that means tell how many numbers you want to change each time. We want to change, let's go by 0.1 this time, instead of by 1. So that's going to change the table, so that now you can see we're going by 0.1, 0.2, we're increasing by 0.1 each time. Okay, so now we've narrowed it down between 0.3 and 0.4, so let's make it a little bit more precise. We'll start at 0.3 now, and we'll go by 0.01 instead. We'll go back to second table, and now we can basically see our 0 is pretty much 0.35 or 0.36. That's close enough. 2 decimal places is usually more than sufficient to be able to find a 0. And you could obviously do that with the other one as well. You narrow down where you're looking, and you go to 2 decimal places, you'll pretty much find it. Alright, the last problem that I want to show is this problem right here. It's a word problem. So it says a package of supplies is tossed from a helicopter at an altitude of 200 feet. So that's where that 200 comes from in that equation. The package's height is modeled by this. So H stands for height. T stands for the time that something's been flying through the air. Okay, where T is the time in seconds. And the question is, how long will it take the package to reach the ground? Well, if you think about it, when the package reaches the ground, what is the height of the package at that moment? When it's on the ground, here's what this looks like. You're dropping something out of a helicopter, and right here it's going to hit the ground. At that point, the height is equal to 0, right? It's not, if it hits the ground, it's not any distance off the ground. So they're basically asking us to graph that and then find the zeros. And the only 0 that's going to make sense here is the positive number, because T stands for time. You can't have, when you graph this, you might have a negative a negative x value, or we'll use x instead of t, but they basically mean the same thing. Negative 16x squared. Now, as I was saying, you might have a negative x value, but it's not going to make sense because x or t is standing for time, and you can't have a negative amount of time, even if you had a time machine. So let's go to zoom standard again, just to see if we get a decent picture. That's not great, but let's just zoom out slightly. And it's still not great, but it's close enough at zoom standard for us to see. Actually, let's try zoom fit just to see if that's a better picture. And we'll zoom in just a little bit. So I'm moving this arrow kind of right over here so we can see. That's a pretty good picture. So we want to know what this 0 is. The 1 on the left side where my cursor is, you can see the x's are negative and we can't have negative time. So let's find that 0. So go to second, calc, and then 0. Left bound means move the arrow to the right, to the left, press enter. Now I'm moving it to the right, press enter again, and now I'm moving it here. And that means that x equals 4.52 seconds. That's how long it takes for that package to hit the ground, 4.52. So that's how to graph functions by hand, and that's also how to graph quadratic functions using a calculator, section 4.2.